Okay, so for the rest of these videos, the outline of this lecture, we're going to talk about three main concepts. So the idea of runtime analysis with a big focus on kind of reviewing some things you might have seen from CSE 143. We'll talk about this list abstract data type, or ADT, and then we're going to finish off talking about design decisions. So before I actually dive into runtime analysis, one thing that I think is really useful for me to explicitly articulate is what I think of as learning objectives for a lesson. A learning objective is, in some sense, a sentence that says, after this lecture, you should be able to something. And these somethings are what I'm hoping for you to get out of this. Now, I think learning objectives are they're a bit optimistic in some sense, since I told you these videos are mostly passive me talking, and that's not how learning works. But after being introduced to these ideas, coming to class to practice them, you should hopefully be able to do these things. These are kind of what I'm hoping you're able to take away from this lecture. So hopefully these learning objectives, which I'll try to be explicit about and what I'm hoping for you to get out of this lesson, will help guide your studying. If you find one of these, you're like, I don't know what this is, that's a good thing to maybe spend more time on. Maybe come to office hours or go to quiz section to talk to a core staff member about. So our four learning objectives for today, explicitly in the camp of 143 review, we want to determine whether simple code belongs to constant, linear, or quadratic complexity classes. Again, it's okay if those words only sound vaguely familiar. We will talk about all of those. This is kind of takeaways at the end of the class. The second is distinguish the list ADT from array list and linked list implementations. We want to compare the runtime of certain operations on array list and linked list based on how they're implemented, and describe the process of making design decisions. Those are our four big takeaways for today. So let's dive in to talking about runtime analysis. So the first thing we think of when thinking about runtime analysis is thinking about, well, how much time does it take for my program to run? What does it mean for a data structure or a program to be slow or fast? And maybe the first idea you might think of is, well, can I just run my program, create my data structure, put in some data, and time it from start to finish? We sometimes call that wall clock time. Like you're looking at the clock on the wall, which I don't have in my house, and timing it. Now, think for a second, why might that not work? Why might just timing code might not work? Take a second to think about that. And you might have lots of possible answers. There's lots of reasons that this can be complicated. One of them is everyone's computer is slightly different. We have different processors, we have different hardware, and maybe something that runs faster on my computer might run slower on your computer. And so there's this context of when we're talking about timing code that's really dependent on the hardware that it's running on. And additionally, computers are pretty complex. They actually run multiple programs at once. So right now I'm running OBS to record this, which actually takes up a lot of CPU time. And so maybe if I was timing my Java program while I was recording this lecture, I'd probably be a lot slower because OBS is hogging up my computer's resources. And so there's really not this nice comparison there. And then also, one thing that's even a little bit more subtle is the time that it takes a program to run or a data structure to do something really depends on the input you gave it. Like maybe on some inputs it's fast, but on other inputs it's slow. And so all of these things, just using time, doesn't really quite address any of those. So our general approach to thinking about runtime, thinking about efficiency, is counting how many steps a program takes to execute in terms of its input size n. So we're going to essentially try to come up with a number that describes how many of these abstract idea of steps are taken whenever it wants to run a program, run on an input of a certain size. And so as a bit of a concept review from 143, we usually introduce the concept of efficiency, which is the measure of some computing resource used by some code. Most commonly, when people talk about efficiency, they assume we're talking about time. So how much time does it take for a program to run or an operation to happen. But there's lots of things we can mean by computing resources. We can talk about space or memory. How much RAM does it use to complete a computation? It could also be how much power it uses, either from a very micro scale, if my computer isn't very powerful, to the very macro scale when we're talking about big data centers and using kilowatts and kilowatts of energy to do some computation. So efficiency can mean whatever you want it to mean, whatever context or resource you care about. Now, but again, for our purposes of discussion, we almost exclusively will talk about runtime, how much time it takes the program to run. But again, not trying to measure the exact number of seconds or milliseconds. And what we're going to do is we're going to measure the runtime in proportion to the input data size n. So we want to report kind of the runtime in terms of if you give it input of this size, this is approximately how many steps it'll take to run. And if you doubled that size, you get a good idea of how many more steps it would take. And so we're going to care about this in terms of growth rates, how much longer it takes something to run if you increase the input size. And so one of the strategies we do when we think about counting these number of steps, we kind of idealize a lot of things. We kind of brush a lot of small details about how computers actually work under the rug, and we make some simplifying assumptions. Every simple Java statement takes the same amount of time to run, like a print statement or 1 + 2, or just any simple line of code just takes 1 step, whatever a step is. If you're calling a method at any point, that method call is the total number of steps taken by that method call is the number of steps in its body. So if you have a method with 3 steps in it, every time you call that method, it will make your program take 3 steps. And loops are just the number of repetitions times the number of steps in its body. So if you have a loop with 5 steps and it repeats 4 times, you do 5 steps 4 times for a total of 20 steps. And again, this is idealizing a lot and hiding lots and lots of details, but this is generally the approach we take when talking about efficiency. So here I have some example codes to make this a little bit more concrete. When I just say something like a equals b plus 1, we say, hey, that's a single line of simple code. It's just constant time. It takes 1 step. If you have a loop that loops from 0 to n, and inside of it, it does 1 step, well, it does 1 step n times. It's going to run n times. And so we're going to say it's on the order of n steps. And we call that linear time because it's on, well, that'll make a little bit more sense when we see some notation, but we call that a linear complexity class. And then maybe imagine you have nested loops where both of the loops go to n. Well, on the inside, its body has 3 steps, and this body with 3 steps gets run n times by the inner loop. That's a total of 3 n steps for just the inner loop, and it runs that inner loop n times, so it's going to be 3n squared. And whenever we talk about things being n squared or squared, we call those quadratic. Now, we actually, one of the reasons we get to be so hand-wavy with these things, or like this is 1 step or whatever, is we actually throw away a lot of information when we actually report what these runtimes are. We end up ignoring constants like 3. Like when I say 3n squared, I would actually just drop 3. The reason is this 3 is completely arbitrary. It came from the fact that I said 3 lines of code equals 3 steps. When in reality, the computer executes millions of steps or for some instructions and maybe 1 step for others. And so it's all kind of just made up anyways. So we just get rid of, like, I'm not very certain about this number 3. And this idea of n squared now, just reporting n squared, gives me a much better idea of how this algorithm scales. I'm saying its runtime is on the order of n squared, but I'm not making any guarantees. It's exactly n squared or exactly 2n squared. And the way we report this is we use this big O notation. We say, write a big O, and then in parentheses, we put the n squared. To say, I did this counting measure and got something like n squared, where n squared is the biggest term. And so I read this as big O of n squared. Don't worry, this was very hand-wavy. We will come back to this again, talking about how to be a little bit more formal with these definitions and how we do this counting. But I just wanted to review this idea of counting steps because it's going to be useful when we think about comparing the list ADTs. And the last thing that is generally introduced in 143 is thinking about complexity classes. So when we make these big O of n squared or big O of n, we usually think of many algorithms that fall in this complexity class. So it's a category of algorithm efficiencies based on the algorithm's relationship to the input size n. And so there are lots of functions that you could have of n. There's an infinite number of them. But there are some oldies but goodies that we generally see pop up all the time. One of them is constant time, big O of 1. That means no matter how big the input is, it takes about the same amount of time to run. And we drop constants in our reporting, so we report it as big O of 1. So if you double the size of n, the runtime's unchanged. We also have the linear complexity class, a big O of n. If you double the input size, it should take about twice as long to run. You can see down here in this graph, the number of elements here is n. So as you go to the right, n is increasing. Oh, whoops, did not mean to go forward. Oh, I can't show my pen here. As n goes forward, n is getting bigger, and you can see constant time always takes the same amount of time. O of n is slowly increasing, but then when you get to this quadratic one, O of n squared, every time you double the input size, the runtime is going to quadruple, because 2 times 2 is 4. And so this thing blows up really quickly. And there's some algorithms we'll talk about later that blow up even way faster than that. And so complexity classes tend to be a good framework to think about how you can maybe bucket algorithms when you're comparing them in terms of runtime. And so we will use this when we go into comparing different data types for their various operations.